Hello, everyone. My name is Lu, and I'm software engineer at Mysten Labs. Oh, yeah. Sorry, I forgot about this. And in this presentation, Brad and I will walk you through native bridge and cell network, respectively. The title of our talk, Traversing the Sui Nexus, reflects the core commission of both projects to build connections of Sui. The journey of Native Bridge began last November on GitHub and Sui Forum with a proposal. And then since then, we have made significant progress. Today, I'm feeling super excited to present the Bridge team and then share it with you. Without further ado, let's begin. We will start with the most important question, or one very important question: why Bridge? Why Native Bridge? It is driven by three primary objectives. First, enriching the bridging infrastructure for the Sui ecosystem. And second, Sui has been endlessly introducing disruptive innovations in this industry. We expect Native Bridge to be used as a tool to leverage the latest tech on Sui and to offer much more enjoyable bridging experiences. Later in my talk, I will highlight a couple of use cases that will be non-trivial to achieve on our chance. Last but not least, we want to use Native Bridge because it's a dedicated bridge for Sui network. We want to use it as a tool to provide community support. So for example, we will use it to assist the builders to migrate their existing chains that previously launched on other chains over to Sui. Now, this entity goes by the name Native Bridge. But what does native, quote-unquote native, signify exactly? And how native is it? There are two aspects that make this thing native. First and foremost, this bridge will be safeguarded by the same group of validators who secure a Sui network. In other words, the native bridge and the Sui network operate under the same set of security parameters. Or to make it really simple to understand, if you trust the Sui network, then native bridge is trustworthy to you as well. Secondly, the move code of native bridge resides in the Sui framework. So this has two implications. First, they have easily memorable IDs. For instance, bridge object will be 0x9 and the bridge package will be 0xb. Two, it follows the same framework upgrade flow as other core components of Sui. So it gives it enhanced security when it comes to code upgrades. We just outlined the grand visions of Native Bridge, making bridging really fun and then providing community support, so on and so forth. Now let's pivot our focus a little bit to the more immediate horizon and then discuss Native Bridge V1, which is going to launch pretty soon. In Native Bridge V1, the cornerstone feature is token transfers between Ethereum and Sui. By default, it will accommodate token transfers of USDC, USDT, ETH, and Wrapped BTC. It's notable that this list of supported tokens may expand as we approach mainnet launch. And additionally, we can dynamically add tokens through governance actions by validator committee. Token transfers within Native Bridge are also operated by the validator committee. As mentioned earlier, the entirety of bridge security is underpinned by this committee's vigilance. Here is how this process works. This is a 10K foot overview of Native Bridge architecture. So you have the move package on the Sui side. You have the Ethereum contracts Solidity contracts on the EVM part. Users interact directly with this contract to deposit and claim funds. The off-chain part, each validator will run a thing called bridge node. These bridge nodes are responsible for monitoring on-chain events, signing, aggregating signatures, and advancing the token transfers on the destination chain. Additionally, bridge nodes are also oversee the governance of the bridge of this bridge, such as like upgrading the Solidity contracts, adding new tokens. Today, however, we'll gloss over this part because it's not directly user-facing. One more thing to note is bridge client, which is not like really illustrated here, but there's a thing called bridge client in this bridge node, and that component is responsible for collecting signatures from the bridge nodes. This part, interestingly, this part is permissionless. Now it has What does that mean? This means that any individual service can run their own bridge client. to directly communicate with the bridge node and then facilitate the token transfers on the destination chain. This design choice brings the native bridge liveness and decentralization. Moving on to our front-end part, it is still work in progress, but we're thrilled to give you a sneak peek into its future interfaces. Users can initiate and complete the transfers on the front end, which is very easy to imagine. And then once the user initiated the transfer, they can monitor the real-time progress. Furthermore, with the transaction history tab, a transaction history tab give the user a visibility into the past transfers. So this is particularly useful for locating pending transfers, especially when you accidentally close out the tab when the transaction on Ethereum is still pending. Beyond this dedicated website, we are also eager to see Native Bridge integrated across a variety of protocols and frontends. The unique features on Sui open the door to a number of interesting experiments you can try on Sui. For instance, with PDB, the users can claim the funds and ape the funds into DeFi protocols in one single transaction in one click. Furthermore, by sponsored transaction, all of these operations can be covered by the protocols. This is not only enhance the user experiences, but also helps drive the user acquisition and liquidity growth for those protocols. This level of integration is feasible because, as earlier mentioned, the bridge client is permissionless. Fundamentally, any entity, whether a front-end or protocol, can act as this client. Now, let's take a moment to assess the current progress we have made so far and what's coming up next. As of today, majority of the implementation in V1 is down. And then they are currently being audited by AutoSec and Zalic. It's worth noting that the front-end code will undergo its own set of audits to make sure everything is top-notch. And looking ahead, we're looking to launch testnet in Q2. Once we have bridge testnet in Q2, we will initiate the bug bounty program. And then after we collect enough valuable user feedback, and then uncover any bugs, address any bugs uncovered, ensuring we're fully confident in the system's robustness, we're going to roll this out to mainnet. But this is just the beginning. As we move towards V2, there's much on the table to be done and enhanced. Our goals include making the large transfer experiences really nice, and then accommodate the dynamic bridge committee management, provide fresher price update. Beyond this, we're also open to incorporating more chains and then adding more functionalities if community demands them. Now, this concludes the section for Native Bridge. Thank you all for your attention. Now, let's welcome Brad to the introduction of SCION Network.
Thank you. Mic on? You guys can? OK, great. All right. Well, thank you, everyone. I'm Brad. I'm a manager at Mysten Labs, and I lead all the infrastructure teams here. And go. There we go. All right, so I'm here to talk about the SCION network. The thing I want to propose is how do we think about and what's the problem with running an L1 blockchain on the public internet? Well, public networks are generally pretty messy, right? They have inherent cyber risks, but if you were to go to private networks, they are very costly and inflexible. Distributed networks depend on a very much secure global connectivity. So as communication patterns are highly distributed with many different entities, typical industry solutions are not applicable and result in high costs and a lack of flexibility. Defense solutions generally don't provide strong protection against routing or targeted attacks, and unreliable networking leads directly to quantifiable monetary losses. In addition to a lack of strong defense against attacks, single provider solutions contradict decentralization. So here are a couple examples of the types of network congestion issues and attacks that we've had to deal with. In the early days of DevNet, I think back in probably May or June 2022, we wanted the community to run as many full nodes as possible in order to test out our software, make sure a bunch of things worked and stuff like that. So we made a call out to the community that said if you run a full node, you might be able to participate in the incentivized testnet. Well, the community certainly answered. They ran 10,000 full nodes. And we had DevNet running in a very small EKS cluster of 4 nodes. So that was quite an experience. So I don't think DevNet necessarily went down because of this, but it certainly wasn't very usable. So it was totally self-inflicted, but it gave us a healthy dose of what can happen in the real world. And I do remember our AWS rep at the time contacting us to congratulate us on the traffic, and also tell us about the upcoming invoice and things like that. So, second example I want to point out is what's continuing to happen in more sophisticated ways is the DOS attacks that are happening on the testnet faucet RPC endpoints. So they kind of ebb and flow, but they also vary in sophistication, but they keep happening, right? And we really want builders in testnet to be able to build. So you need to be able to get gas coins, you need to be able to use it, and stuff like that. And so each time these attacks come by, we're having to do different things to make sure that they can't pummel the network and make the experience bad for everybody else. We've tried a number of vendors. We've had a number of solutions in place, but we haven't really found a great solution there. So let's talk a little bit more about decentralization. So we really want to avoid centralization for a network defense perspective. Most in-defense network solutions have a dependence on a single provider. For example, standard DDoS defense solutions and SD-WAN. But we're not the only ones running a piece of this network, right? There's many validators, there's many RPC providers. They're running across different hosting providers, different data centers. So even if we protect the Mysten nodes, the rest of the network is still exposed, and that's not a great situation to be in. So a lack of decentralized solutions poses a major challenge to Web3 networks. So what's the solution for all this? The solution is to build on a secure public network infrastructure. So I'd like to introduce SCION. SCION is the first clean-state internet architecture designed to provide route control, failure isolation, and explicit trust information for end-to-end communications. It provides an alternative to BGP, offering high reliability and resilience despite attacks. High-speed global routing convergence, fast failover in the case of link failure, and native WAN multipath communication. Performance-wise, how does this actually compare to BGP? Well, on a per-path basis, SCION overhead's about 200 times lower than BGP, about 1,000 times lower than BGP-sec. Time to connectivity in SCION is over 3 orders of magnitude faster than BGP. The iterative convergence approach in BGP takes minutes to converge with a fully updated forwarding tables in case of small network changes, and sometimes even hours in the case of a large-scale outage. SCION itself has been in production use since 2017 and is thoroughly tested and analyzed. It's being used in several critical infrastructures across finance, healthcare, and energy. So here are some of the additional SCION network features. From an availability perspective, SCION has strong defense against distributed denial of service attacks and routing attack prevention. The network is designed to recover quickly in the event of faults. And since it's a decentralized network, it has no global kill switch and has local control of trust routes. From a transparency perspective, SCION can do selective forwarding given the built-in path awareness. This leads to the ability to geofence portions of the network or route around potential problems. And from a security perspective, it has built-in encryption and hijack prevention. One of the main use cases that we're building for is specifically validator-to-validator connectivity. The consensus traffic is very latency sensitive, and SCION is a huge benefit here. Another is full node to validator traffic. We already have this running in a test setup, but SCION can help mitigate DDoS attacks from a rogue series of nodes using the full node to validator RPC interface. Beyond this, we envision having full entity to full node connectivity. An example could be a gaming company on Sui obtaining an edge subscription from their ISP so their users can benefit from the latency and security properties of the SCION network. Effectively, a connection to the public SCION network has a similar security property as a traditional leased line. We envision the entire Sui ecosystem to benefit from the Sui network in the intermediate term. So what does this look like in practice? So SCION offers a failure-independent public WAN operated by known network providers side by side with the regular internet. There are no supply-side bottlenecks as SCION allows reusing existing infrastructure and supports incremental deployment of new internet architectures. Together with Intercloud, Cyberlink, and Enterprise systems, Mysten has built 2 global SCION rings offering triple redundancy together with regular internet communication. This offers one hop IP to both rings, which can cover roughly 70 of the validators in testnet for now, and others will still be able to connect. With this architecture, we can tolerate 2 link failures in the router failure. Primarily, initially this will be used as a backup to IP, but eventually we'll be able to change the routes and make it the primary interface. As the Zion network has built-in defenses against global routing and DDoS attacks, the resulting infrastructure provides unprecedented availability. The system is easily deployable and will provide strong security at a low cost, making Sui the most available blockchain. So what does it look like for a specific deployment? While there's other deployment approaches available, the preferred approach deploys the Anapaya Edge software appliance, which requires 2 vCPUs and 2 to 4 gigabytes of memory on an already provisioned bare metal Sui validator host, sharing a network interface between both the edge guest and the host with low impact on performance. So there's only a few components here. We've got the Anapaya Edge VM. It's a Scion router and has a networking stack that connects to an upstream Zion provider and forwards traffic. It's provisioned as a virtual machine. We've got the routing daemon that updates routes on the host based on information provided by the router in the Edge VM. A bridge interface, which will provide management communication between the guest VM and the host applications, and then hardware-based virtualization of the public interface to share it with the Edge VM. So what's next? Our primary goal at this point is to protect the Sui network with Zion connectivity. First testnet and then mainnet. This will require onboarding more global carriers and working with the validators and node operators to get them connected to the Zion network. The Zion and production engineering teams at Mysten will be working closely together to help build the network out with validators and node operators throughout the rest of 2024. We are currently rolling this out on testnet, so stay tuned for further updates. If you'd like to learn more about this, reach out to Adrian Perig, who's back here today. Hi, Adrian. The Intercloud folks are also here somewhere. Yep, back there. And so we'll all be around all week. So glad to answer questions on this and talk more about it. And with that, thank you. Leave you with this meme of a Cappy Sui on Zion.